We're going to continue our workshop agenda. Thank you, Dr. Craig, for your time today. And the next talk is from Dr. Brian Johnson. The title is Power Grid Operation and Control and Resilient Architectures. Dr. Brian Johnson is a university distinguished professor and the Endowed Chair in Power Engineering in the University of Idaho, Department of Electrical and Computer Engineering. Dr. Brian received BS, MS, and PhD degrees in electrical engineering from the University of Wisconsin-Madison in 1987, 89, and 1992, respectively. He joined the University of Idaho shortly after completing his doctoral degree. He was a chair of the Department of Electrical and Computer Engineering from 2006 to 2012. His teaching and research interests include power system protection, power system transients, HVDC and FACTS, and resilience controls for critical infrastructure systems. He has advised over 200 part-time and full-time master's and doctoral students. He has published over 170 papers in journals and conferences. Dr. Johnson was the chair of the IEEE Power and Energy Education Committee from 2014 to 2015, and is currently the chair for IEEE HVDC and FACTS SU 2015, and Dr. Johnson is a registered professional engineer in the state of Idaho. Dr. Brian Johnson, it's an extreme honor to have you as part of the resiliency workshop today. The floor is yours. Thank you for spending your time this morning with us. Let me see if we can share your screen. Yes, we can see your screen. You are muted, you're muted.
Yeah. Okay, well, thank you for the introduction. So I'm going to give more of an overview for power grid operation and control and talk a little bit about power system apparatus. Part of the purpose for this talk is that usually when we talk about resilient controls, we have a fairly diverse background. So we'll have some people that are subject matter experts in power systems and some that know power system operations very well, some that really don't have a very good knowledge on this and are just kind of getting started. So for some of you, this talk may seem kind of like a review or talking about things you already know or that you know more deeply than this talk is going to discuss, but this is to try to prepare a broader audience for the presentations that are coming up. And so when we talk about what I'm going to talk about is give a basic overview of power systems, talk a little bit about equipment we see in a system, talk about operation and coordination for a complex grid, talk about how things are evolving and how things are changing. And we're going to talk about this in terms of resilience. And so when we started doing the resilient controls course that Craig referred to, and then later when we worked on putting together the book, we chose to use a power system as a use case. Resilient control should be applied to any cyber physical system that has distributed communication and controls and has automation support for human operators and have the human in the loop. Craig talked about this in a little bit broader sense. We chose the power infrastructure partly because it's pervasive. It's very central to pretty much everyone's lives. Most people think they know something about the power system, so it was also a good starting point to talk about. It also makes use of human operators and with an increasing amount of automation support. Also, when there are problems with the resilience of the power system, people really notice it. And so when we talk about power system control in the context that we're going to hear from in this presentation and later ones, we have a range of timescales going from 60 hertz cycles, so periods of tens of milliseconds where you've got to seconds to a few minutes where you have autonomous controls because a human operator isn't in a position to really respond to that. And then you have going to minutes to tens of minutes to hours where the operator response is really much more involved. And then you have local measurements and a communication infrastructure that are taking information to this operator and then going back to the decision points. And so when we talk about a power system, the first question is, what is the objective of the power system? I usually talk about this when I am talking to undergrad college students or even graduate students, is they get, sometimes people, will, especially at the student level, will get so caught up in just learning to do this analysis that they forget that the purpose of the system is to transfer power from power sources or energy sources to end users. And we need to balance the supply with the load. Load varies, and generation is increasingly starting to vary as well. Renewable generation with wind and PV is generally increased that trend. But even as you started seeing third-party generation come onto the system that was not dispatchable. So over the last 20 years, there's been a big increase of third-party generation connected to the power system. And this actually goes back to legislation in the 1970s that that non-dispatchable generation can turn off unpredictably. At times you might not expect it to disappear. So when we talk about balancing the supply with the demand, one of the things to remember is that basically anything that's generated has to be used at that instant in time. There is some storage, and we'll talk about that later in the presentation, but compared to the total amount of energy that's being transferred between sources and load at any instant in time, the amount of energy storage in the system is actually quite limited. And so historically, if we looked at a power system, we would have power plants, which would probably be a mix of oil plants, coal plants, starting in about the 1970s or 1980s, you started to see an increase in natural gas that really accelerated later on, and then some nuclear power plants. Generally, these plants were all owned by the same company that owned the transmission system and owned the distribution system that got the power to the end users. And so this was all owned and maintained by the same people, and they had somewhat limited visibility. So if we go back to the early 1970s or 1960s, if somebody at a utility control center wanted to know what the voltage was or how much load was going through a given substation, they would need to get on the phone and talk to a human operator at that substation and have them read the meters for them. So they did not have a lot of communication. They had physical measurements from the system, some that are a quasi system-wide quantity like frequency, and that was actually used as basically a communicated control signal because it spread through the whole system. And as we'll see in the next little bit, this has changed quite a bit as we've been able to have communication come into the system and affect how it's operated. And as John Gibson talked about in his talk, how legislation has affected how some of this works as well, both from state legislatures, the federal level, as well as state public utility commissions. So when we talk about generation, historically, much of the generation was from synchronous machines, and there's still a very large percentage of generation is from synchronous machines, whether it's coal or natural gas, nuclear power plants, or hydroelectric. So we have machines that may range from a few megawatts to over 1,000 megawatts. And we may have plants that have multiple generators at that plant. So it's not just one machine at a given location. Most of the synchronous machines are dispatchable, that there is a human operator at a utility that has some role in sending set points to them and scheduling them. These are generally producing power at a relatively low voltage, and then it's stepped up to a transmission voltage level. So when we look at this the previous figure, where we see these transformers are going to be at the power plant, and then we're going to have the transmission system at higher voltages. And so with these synchronous generators, the speed that the rotor is turning is aligned with the power system frequency. And so they have a closed loop control system that will effectively measure the system frequency and use that as a measure of how well they're balancing the load. So if the frequency is too high, that means that the source of power, source of energy is in the whole, as a system-wide quantity, is exceeding what's being consumed by the load. If the frequency is too low, there's a deficit on generation. These synchronous machines have a large mass that's rotating at a high speed, which stores kinetic energy. And a lot of times we think of that as inertia when we're talking about a power system. And so if there's a sudden change of load, or if a power plant somewhere suddenly trips offline, or a transmission line has a short circuit and opens, that initial change of energy is provided with an inertial response from that rotating mass. As the transition has gone from a lot of steam-based plants, so whether it's a coal-fired plant, a nuclear power plant, or something similar to that, to gas turbines or renewable energy with inverters, we're losing some of the spinning mass. So there's a lot of spinning masses associated with the various stages in a steam turbine. And so some utilities have talked about taking decommissioned steam plants and converting them into reactive power sources. And when they make them into these reactive power sources or synchronous condensers, if they cut away all of the mass associated with the steam turbine, they actually have a lot less inertia that they can provide. So some are actually adding flywheels to those. And so with the synchronous generators, there's usually a control response that will rebalance the system following some sort of a change of load or change of supply. And there's a local response, but then there is a central response that will come first from an autonomous system, and then it will be backed up by a human operator to come up with a better system-wide view of it to resolve this. And so we've seen a lot of increase in renewable generation sources. There's still a large amount of hydroelectric generation, but we've seen a lot of increase in wind generation and photovoltaic generation in the last 20 years, but it's really accelerated in the last 5 or 6 years. And so the wind generation and photovoltaic generation rely on power electronic controls, and power electronic controls are playing a bigger and bigger role in the power system. So if we talk about like a computer or your phone, basically you have something that takes input data, it processes that data and produces processed output data. And it receives some power, and it may receive a control input. Something that's a power converter is going to have power that's coming in at some voltage or current or frequency. It's going to process that power and then produce processed power that might be at a different frequency. It may be regulating something. It may be regulating a specific amount of power. And it has a control input. And so this is basically going to be some sort of information processor. So there's a lot of interactions when we start seeing that this depends on power, this depends on information. So when we talk about photovoltaics, we're going to have a DC to AC converter that connects it to the power system. And there are just some different designs for that. When we talk about wind turbines, a lot of the wind turbines that you would see driving around are going to be ones that have a doubly fed induction machine. They're going to have 2 converters, and these converters regulate the response of this. And these have become the most common ones for land-based systems. And with this, that they can give very precise, very fast control and very fast disturbance response. That produces some challenges for power systems operation. And this is going to be controlled to try to get the maximum power available out of the wind resource at any instant in time, and to try to get that response as quickly as possible. And we'll also see another type of wind turbine where the entire output is converted to DC and then converted back to AC. These are more common with offshore applications. In some areas, they also get used in onshore applications because you might have high risk of subsynchronous control interactions. Now, when we talk about these having fast control with a synchronous generator, the time constant you look at for actually engineered control response, where you've got a closed loop control system, are generally going to be a half second or longer. For these types of converters for wind or photovoltaic, that control response time is going to be on the order of milliseconds. And so they're going to look like they have, from the power system point of view, they're going to look like they have nearly instantaneous response. And that means that that effectively their equivalent to an inertial response is going to be very, very short. There's been some move to try to put in some controls on those. When these sorts of systems first started to see more use in the power system, the initial thought was, we want these things to shut off in the event of a disturbance. What rapidly became an issue was, no, we want these to stay on, because they are such a significant part of the generation on the power system that if they shut off, it hurts system recovery. So at the distribution level, there was an even bigger push that these things should shut off if there's a disturbance. And in recent years, there have been some near misses where some utilities have had widespread loss of these systems that have shut off because of control response, or basically human error in setting up their control response. And so that's something that has been a kind of an active issue to try to rectify that situation. I mentioned energy storage a few minutes ago. So there's fairly limited use in North America, but it's rapidly increasing. There are a lot of older hydroelectric facilities, and these are pumps. Most of these are pump storage facilities where basically at times of low demand, you're pumping water up to a reservoir, and then at times of high demand, you're reversing that. Some of the older systems, so one that's in central Washington or north central Washington is Banks Lake at Grand Coulee Dam. That system, the way that was set up is that they could start the pumps once a day. And the thermal shock from starting those pumps was such that they couldn't do repeated starts. About 15 years ago, they refurbished those so that they have more flexibility in the operation. But when they're pumping, they pretty much just pump at one rate. When they're generating, they can control them like any other generator. And so some of these dedicated pump storage projects are ones that have been built by federal agencies. Some have been built by utilities. There are also some merchant projects that have come in. But when you look at most hydroelectric facilities, most of these are run-of-the-river facilities, and you're trading off with other users of the water as priority for the water. So there's not a lot of storage available. There are other storage technologies, and this came up with some of the questions in John Gibson's talk this morning, is batteries have become are becoming increasingly commonly used. Some utilities are putting them in for transmission level applications. And so most of the ones that are going in are lithium ion batteries or variants on those. There are a number of flow batteries that have gone in. There are other technologies, so fuel cells or flywheels. Several of the vendors of flexible AC transmission or FACTS devices have started putting ultracapacitors on the DC side of those and using them to provide a little bit of inertial response if there's a disturbance in the power system. And so that's starting to see more application in North America as well. When we talk about energy storage, you need to rate it both in terms of instantaneous power, and so some of these systems are designed so that they charge slowly but can discharge quickly, and that's related to a specific application. So if you have an application where you're mostly doing backup power, that's what you might do. If you're trying to mitigate power swings or disturbances on a power system, you might need it to be able to charge quickly and discharge quickly. You also have energy ratings that go with this as well. So John talked about the battery that was built at Schweitzer Engineering Labs for that. The primary purpose was for backup power for their manufacturing facility, but they also used it for doing some grid services as well when it was running. And so that was a 1 megawatt, 3 megawatt hour system. So that could supply 1 megawatt for 3 hours. And so that depends on how the storage itself is rated. But how these are rated and sized is very application specific. And the other thing to think about when you start rating that is, where do you have it sitting on state of charge? If you have it sitting at 100% state of charge or 95% state of charge all the time, you can't absorb much power if you need to in a power system. And so again, very application specific. And this is kind of a busy slide, but this has timescales, and we talk about energy. So megawatt seconds or megawatt hours, and then power transfer. And so this is looking at some different applications, whether we're doing power quality, transmission stability, frequency control. So we have and power and energy increase when we start going into some of these applications. And then one of the questions is, do we do a lot of small batteries? Do we do one large energy storage system? Who owns it and who controls it is also another question. And what are the signals that drive it? And so these are all things that need to be looked at when you're sizing these. So the next step of the system is transmission. And so when we talk about a one-line diagram for a power system like this, where we see generators here, this is not a single generator at any of these sites. This is usually going to be multiple generators, and there are probably going to be multiple transformers. And when we talk about a load like this, this is an equivalent to a much larger system. But what are some things that you can look at for how this system is operated, how this system is designed as you modify it to operate the system better? Do you look at cost? Utilities will often look at reliability. And so there are many things that come in with that. And now there are changing needs. We're seeing renewable energy systems that are being installed in parts of the system that were often kind of the fringes of the transmission system, so the transmission system wasn't very strong. And so there's been a need to do a lot of reinforcement and building new lines. There are some cases where you've got photovoltaics that have energy storage added. In some cases, the energy storage system is a discrete system with its own inverter. In some cases, it's on the same DC link system as the photovoltaics. And these systems are coming in, and a lot of them are being put in by third-party groups that are funded by venture capitalists. And so there have been increasing requirements on how to set up interconnection agreements to think about how to maintain what's effectively affecting defining things related to resilience of the transmission system, so that the previous idea where these things have a hair trigger and shut off if almost anything happens in the power system, now they have to stay on for a certain length of time. And that's a minimum length. If they can stay on longer, that's even better. So when we talk about controlling the transmission system, there are limited options to directly control line flows. There are lots of things that have been proposed and even tested as prototypes over the years, but it's very hard to make a budget justification for putting a lot of the technologies in. That's the environment for some of those is starting to change. But ultimately, the current flow in the power system is based on physics. And you can't force the current to take a certain transmission corridor based on a contract. It's going to follow Kirchhoff's current laws as it distributes for the power system. And so you have some lines are going to be limited purely by thermal limits. Some are going to have stability limits under different time frames. And so those are all things that have to be considered with operating the power system. And so you have increasing challenges for the power system because you're doing larger power flows over long distances. And the timing of those is changing. So, for example, from the northwest to the southwest, there's a very high capacity HVDC line, and there are also a bunch of AC transmission lines. When those were built, the idea was that in the summer, power would go from north to south. In the winter, it would go from south to north because there was a lot of excess generation in the winter and a lot of people heated with electricity in the northwest. Now, most of the year, power flows from north to south during the night. During the day, if it's a sunny day in California, the power transfer goes almost to zero. And then it ramps up quickly as the sun goes down and then stays near maximum power transfer capacity going from north to south all night. And then it starts to go fall during the day. And so when you start looking at the system, you have to say, oh, how is this going to respond to a disturbance? How do you ensure that that HVDC line trips, that we have enough capacity to still maintain the system in the south if we're at the peak transfer? And so there are lots of limits that get looked at from an operational planning point of view. The next level of the system is a kind of a sub-transmission system. This is at lower voltage levels, shorter lines, but it's basically connecting the transmission to the distribution substations. But it's still something that will support power flow in two ways. Then there's a lot of distribution system. So most utilities, the majority of their circuit miles is distribution system. And they have a lot of apparatus that's installed at the distribution level and a lot of investment sunk into that. And so major changes to the distribution system are a challenge because of the cost of trying to say we've got all this apparatus to deal with. Most of these systems are radial with normally open switches that can be closed to make connections. Often they're somewhat unbalanced, and then historically they were designed assuming there are no power sources connected to that system. So this is kind of a historical distribution system where we've got the source coming from the utility, and then we've got laterals coming off of a main trunk, and then we have transformers that supply multiple houses. Now we're starting to see distributed generation coming in, so rooftop solar, other forms of community solar, other things that are coming in. Now, when I talk about having these connections, so for example, if we look at the system from here to here, we may have a case where we have a connection between these two. We have a switch that's normally open. And then if there is a short circuit on this part of the system, we would open a switch here and we would close that switch and we could feed the end of this feeder from this. So when utilities have had these connections for a long time, originally these were set up that they would basically roll a truck and have a human go out and make these connection changes. There's an increased use of having automation to make these changes instead. Also, there's a lot more communication so that there's visibility. So for a lot of utilities, for most of the time that we've had power systems, if there was a fault here and all of these people here were interrupted, the way the utility knew they were interrupted was when people started calling to say that their power was out. Now you've got monitoring, providing intelligence and providing information back to the control center. So now they know that they've had an interruption instead of having to wait. So now they can respond more quickly. Some larger systems will have, especially if they have a dense urban area, they may have a meshed distribution system. And that affects some of the control and protection principles for that. But that in some ways, other distribution systems are heading that way because of distributed generation. Okay, so now if we continue with performance expectations. So just a second, let me get rid of. So when we talk about performance expectations, one thing that for most utilities, they're expected to maintain frequency to a very tight tolerance. From an end user point of view, most residential users don't really notice that very much, especially since not many people have clocks that are based on synchronous motors anymore. But they're also expected to maintain voltage magnitude to a very tight tolerance. And reliability is basically a given. The utility industry has been so successful with reliability that people pretty much take it for granted, and if the power is out, it's usually it's a surprise and causes a lot of problems. The other thing is trying to keep the cost as low as possible, and which also often means keeping losses low. And so part of maintaining that reliability is power system protection. So this is going to be detecting short circuits in equipment and responding to it and isolating as little of the system as possible. And also try to keep the interruption as short as possible. Now, this is one of the areas where human error comes in. So anytime there's a protection operation on the bulk power system, utilities are expected to evaluate it and see, was this a correct operation? And there's still a surprising number of these are due to incorrect settings. And in a few cases, these settings errors have led to cascading outages. And so normally we want protection responses to faults, abnormal operating conditions, and the expectation is usually the relay is going to detect the fault in less than a cycle. So in about 15 or 16 milliseconds. And then it will send a command to open a breaker. At the transmission level, you may have the detection and the breaker open in 30 to 50 milliseconds. At distribution system, it's generally a little bit slower, so you may be getting into hundreds of milliseconds in response for a lot of systems. And then to provide redundancy, there are overlapping zones of protection. So for this transmission line, for example, there's going to be backup protection. So if this breaker fails or this breaker fails or the relay fails, something else is going to send a command to make sure that you isolate that, but you isolate a little bit more of the system. There's often going to be redundant relays. So for an important generator station or for an important transmission line, there's going to be multiple sets of measurements. There's going to be multiple different relays that are using separate measurements and have a separate communication system to the circuit breaker to ensure that there is no single point of failure that will prevent interrupting that fault. So some of the schemes use current measurements and just say if the current exceeds a threshold, they respond. They may design to coordinate with fuses. You see that extensively at distribution systems. They'll also calculate effective impedance looking into a line, or they're going to do differential protection where they're going to sum the currents going into a zone. The differential protection is a very effective form of protection. It has some weaknesses, but the relay vendors have designed solutions to work around most of those. Now, when we talk about a power system, we're moving from a regulated monopoly that was set up to avoid duplication of apparatus, but now there's a lot more use of markets that could be regional and covering some fairly large regions that have led to a diverse generation portfolio and then possibly regional transmission operators. And so you may see that utilities own and maintain the transmission, but a regional transmission operator may actually be more that's controlling that system. Utilities started making connections to their neighbors in the early 1900s and the mid 1900s. And then by the 1960s, there started to see some cascading blackouts that because of these connections. And so this has continued to evolve, but it's led to more national level or regional level control of the system. As I mentioned earlier, supervisory control and data acquisition, providing measurements back to a control center, really go back about 50 years. Computational tools from a planning point of view go back to about 50 or 60 years as well. But then they went from analog controls to digital controls, and we have a lot more data available, and that's made a big impact on system design and system operations. Now, the power system control is, as you go to a larger system, has a very distributed feel. So there are definitely a lot of local autonomous controls that take input from a central control center. And so for very fast response, you do the decentralized automated control. For slower response, you may have centralized autonomous control schemes, and then you have operators and an even slower response. And so part of the goal is where you have human operators, you have the operators do what people do best and don't try to have them do things that automation could do better than them. But you also need to look at what are the failure modes of that automation, what are the blind spots an operator has. And the power system is operated in real time. It's not, so the measurements, the processing have to be done in real time. But one of the things to bear in mind is, what is real time? Real time for what an operator does is different than what real time would be for a protective relay. So for protective relay, real time is on the scale of milliseconds. For an operator, real time is on the scale of tens of minutes often. And so these measurements are taken at high sampling rates, and then they're communicated to the central control center with update rates in maybe seconds. But some measurements are updated faster. When these measurements come to the central control center, they're processed to determine the state of the system, and then there are a bunch of contingency analysis or what-if scenarios performed. To try to improve some of this visibility of the system, people have started using time-synchronized measurements. So most of the SCADA system is set up assuming that we don't have common clocks for all the substations. And so there's an optimization calculation done to perform get the state of the system, and it's over-measured. Time-synchronized measurements can enhance that. It's possible to do a direct state measurement in theory. Very few utilities have that penetration of these time-synchronized measurements and have the reliability of their communication system to support doing that. So most will use the time-synchronized measurements for other purposes for controlling the system, but not necessarily for some of the central parts of controlling the system. And so one of the other things these will do is they will increase observability of the system and provide some sorts of measurements that can't be captured by SCADA because they're updated more quickly. And so they enabled wide area measurement and control systems. So we're moving to an architecture that looks like this, where we have a much more critical communication infrastructure to be able to support renewable generation, support increased automation in the loads, and at the same time reduce operating costs. So with having more computation capabilities in the control center and in the autonomous devices and more communication, there is much more data available. It's updated more frequently. It gives better visibility with a shorter time scale. SCADA systems will miss things. There was a case in California, several cases in California and Texas, where short circuits on a power system caused thousands of megawatts of PV generation to go into momentary cessation where they stopped producing power. And then they came back on when the power system went back into what they considered to be an acceptable state. For the utilities involved, they don't really know how much generation went into momentary cessation. They just know what they captured at those discrete slices in time where they got the SCADA measurements. Some of this stuff, some of this generation shut off and turned back on between SCADA polling intervals. But some of the things that you can gain with having this better visibility and better communication control is you can operate the system with far smaller margins, and you can be more responsive and more reliable. But that's not without risks. So you can operate the power system much, much closer to the physical limits, but you're relying on the communication to do that. What happens if you have a problem with your communications? You have the risk of cyber attacks. And so now the resilience of the communication infrastructure is as important as the communication, the power infrastructure. Now, a lot of utilities own most of their communication infrastructure, but there's still some that is leased. And there's, as was talked about in our talk during the first break, there's also some possible bridges between communication systems into the operational system. So when we talk about the operator interface, the operators receive process data from measurements. So it's the current state of the system. Are there any violations in the current state? If they've been planning the system properly, that's not going to be an issue. Then when they do all of the what if scenarios, then they're going to see, are there violations? And they're going to take actions to ensure that in the next hours, anticipating how generation and load is going to change, make sure that they don't have, that they resolve those violations. So they can't have multiple violations happen at once to bring down a substantial part of the system. And so you have human machine interfaces for the operators at the control center for the transmission level. Some utilities are increasingly doing this at the distribution level. If you go to a substation or a power plant, there are HMIs, human machine interfaces for the operators there. As Craig talked about, it's possible to provide more and more data to them because we have more measurements. How do we make sure we don't overwhelm them? So from a system operations point of view, when we talk about real and reactive power, real power is tied to frequency, and a lot of that was controlled through generator governors. Voltage was reactive power, which was controlled by generator exciters, plus local controls like capacitor banks or tap changing transformers, because reactive power really has value locally. Real power has value at a distance, but reactive power does not. So most generation is located far from load centers, and so trying to transmit reactive power long distances is inefficient and ineffective. But when you talk about energy balance, if we look at load and generation, we want to see the frequency here. If generation is exceeding load, then we go this way, and vice versa if load exceeds frequency, as I mentioned earlier. And so earlier systems had mechanical governors, and then they went to analog control systems. Now you may have digital control systems at a generator, but basically they're going to do some initial response if the frequency varies. And frequency, as I said, was communicated as a system-wide variable. And so historically, system operators would dispatch large plants, so coal and nuclear plants, and keep them operating at their optimum operating point all the time. They would start intermediate plants as the day went on to supply power during the day, and then they had peaking units that they would use for high demand. If they were in an area that had a lot of hydro generation, they would use those some ways to, some utilities would use them as base load if they had enough hydro. Others would use them to cover changes in load. Some regions, like for example, the Northwest, use the hydro to offset variable generation from wind and PV. But there are some limits. Certain times of year, that's not available. During a year with very high snowpack and a lot of snow melt, there's so much water in the rivers that it all has to go through the dams. They can't hold it back because it's got to go somewhere. And so they have very little ability then. And so there's also some of it, there's some nice things with it. There's some things to be careful of. When we talk about wind and PV, they operate at the maximum available power. They can be quite variable at times. Most utilities have very good weather forecasting to support this, but the weather forecasts still aren't always right. PV tends to be more predictable, but it can have very fast ramps. Wind is less predictable when we start doing over hours. And when I say PV is more predictable, I mean over hours at a time. But wind will tend to have slower ramps. So both are things that need to be considered from the operational point of view. And both you have advantages of regional diversity. So if all the wind is not in the same place, all the PV is not in the same place, they're not all going to move at the same time. And so when we talk about control at the transmission and distribution level, transmission, you'd hear the term energy management system. You would have an automatic generation control system. That's one of the autonomous systems that maintains frequency as a system-wide quantity and will adjust generator set points autonomously, and then the operators will go back and tweak it. And then a lot of regions of the US have independent system operators of some form that are running the transmission system, and they may be running a market, or they may have some other way they're regulating the system. At the distribution system, you're going to have a distribution management system. Some utilities have distribution system operators. Some refer to them as dispatchers. There are different terms you'll see at different utilities. And there's an increased use of automation to try to get faster responses and decrease how long it takes or how often they have to roll trucks out to resolve things. So the automatic generation control will vary, we'll look at frequency, and it will look at area control error, which is exported power leaving a given region. And it will also look at time error. And so these are some things that basically try to recenter the generation to keep the frequency at an ideal place. And so this is usually going to be updated on timescales of seconds in a lot of regions, and this may be run at a utility control center, or it may be run at a regional operator level. And so we have balancing authority. So if we look at the Western US, so we look at, for example, we had John Gibson talk from Avista. This is roughly the footprint of Avista's area, balancing area. So basically, they're the balancing authority of last resort in this. So they have to maintain the balance between load and frequency. So if they have third-party generation in their region and they're not meeting what they promised, then they have to provide the reserve to cover that. And so they need to balance load and generation and net interchange to neighbors, and they need to control frequency or time error. And so they need to be ready to respond to major events like generation trips or other problems like that. And so we'd have control error if we're not maintaining contracted flows over the lines, for example. And so when I talk about reserve, so if we look at the orange line in the middle, this is the forecast that is planned. It's just scheduled 15 minutes ahead, an hour ahead, possibly hours ahead. It depends on the utility. And then there's ability to regulate up or regulate down. And these are the reserve margins that the balancing authority has to maintain, and their operators have to continually make sure that they're meeting that over any period of the day. The blue line is what the load actually did. And so when we get into this area, this would be basically a violation. They did not have reserve to support this. And so they had to get power from somewhere else to maintain that. And so you need to have some way of maintaining that. So you might hear the term spinning reserve, and you have to have generation that can go up and down. And one of the things that becomes an issue is who pays for that reserve. So if a third party is connecting a wind farm or a PV installation to a utility, there's an interconnection charge that's related and includes paying some of that, supplying that reserve. So there's regulating reserves. There's contingency reserve, which is a little bit different, but it's the same basic concept. And so You might have generation, you might have storage. Some regions will use a market to try to help support that reserve. And some may have a reserve sharing group or a power pool. For example, California ISO has contracts with Bonneville Power Administration for helping provide some of their reserve. And so when we're doing limits, we have to have the system be able to handle single, and most of the US, double contingency. So this is what if scenario. So what if this line trips and this line trips, or this line and this generator trip? You don't want to have the system go out. If that equipment, if something does go out and is staying off, then you have to update your calculations with that off. And so to try to get around some of these things, utilities will have special protection schemes or remedial action schemes that are going to be autonomous schemes that will be operate under a specific set of circumstances. Often they're owned by an operator, and then they act when preset conditions are met. What's happened in the last decade, especially in some parts of the country, as we've had this big increase of renewable generation that's been located at places where the transmission infrastructure isn't entirely built out to be able to support that, there's been a very significant increase in need for putting in more of these systems. And the regional reliability coordinators have started putting in requirements on documentation for these, so that all the operators at the different utilities are familiar with what's out there and how they're going to respond. And so abnormal situations, we could have power outages due to natural disasters, failures of equipment, misoperation of protection equipment. Some of this could be misset equipment or human error. And then also there's the increased risk of cyber attacks. So some of the things, as John mentioned, is one of the ways to try to mitigate some of this locally is have microgrids. Now, microgrids can be distribution systems. Some of them can combine transmission and distribution. And so these can have variable generation sources. Until a few years ago, the majority of microgrids operating in the utility industry were basically supplied by rotating machines. There's been, even though if you look at the papers published on it, they assume that everything is renewable in them, but most existing systems that are operating have rotating machines, but that's starting to change. And so when we talk about measures of power system performance, we'll look at reliability as one of the things that historically the utility has looked at, and that's one of the things they're rated on by their state public utilities commission. So the interruptions, the time duration of the interruptions, how often they have interruptions. In some ways, some people will look at this as a distribution type sort of metric, but it is something that they are judged on. Another one that some users are going to look at it more from the point of view of power quality. How do I have voltage sags? Do I have a lot of harmonics? Do I have things that cause my equipment to misoperate? Resilience is just starting to really become a bigger part of the picture from the public utility point of view, public utility commission point of view, and the regional transmission operator point of view. And so, as we talked about earlier, there's been some initial discussion towards metrics, and some people have metrics that they use for it, but it's still evolving. Some of the reliability metrics that we would see are going to be system average interruption duration index. So basically the sum of total customer interruptions. So like, for example, if a residential customer gets interrupted, that's one customer interruption. And that's divided by the total number of customers. You have average frequency index. And so the total number of customer interruptions is a little bit different calculation, and it's divided by the total number of customers served. You have time duration. So if you have 1,000 customers that are interrupted for a minute versus 50 customers that are interrupted for 10 hours, they are going to look very different on these different indexes. So if we look at SAIDI and SAIFI, they look very different than this CAIDI index. And so utilities have spent a lot of time to try to improve their numbers on these, and they've been very successful with this. And they design their systems and they operate their systems towards this. But these are not the same as resilience. And most of these are things that are looked at over a year. So they present the numbers for a year and when their annual reports they give to the Utility Commission. Okay, so this talk was really to give an introduction to some things to think about and kind of set what you're going to hear from the later speakers in context. I know I went really fast through this. You'll have access to the slides. If you have questions, we got a few minutes for questions now, and otherwise, I guess you can you can send questions and I can follow up with them later in the day as you send them.
Thank you, Dr. Brian Johnson, for a nice, insightful talk. I think this was a good refresher course, I think, to get the basics straight. I think it's nice that you took time to go over the fundamentals. So appreciate for the reminders and still talking about some challenges. We have 4 minutes, so we can take some questions. If folks have any questions, please use the chat or the Q&A option, so we can collect questions and ask them. We have a question, I think, okay, can reliability metrics be part of resiliency scoring? Even though they are a little different, but, can some of them can go into resiliency scoring?
Yeah, they can be. They can be it depends on what you're combining when you're putting in the score for resilience. A lot of the reliability metrics are really backward looking. So looking at how have you done in the last year, and based on what we saw in the last year or the years before that, we're going to modify our system to keep those from being as much of a problem. Resilience metrics also need to look at what are the unexpected things, what are the kind of the rare black swan events that happen every 20 years or something like that. How are you prepared for that? So the resilience metric may need to consider the unexpected. And as John Gibson gave a good example of having something where we're not restoring everything to the perfect level, but we're going to have something where we have community centers where we make sure that the essential services are still available for people in the community. And so that would be maintaining a level of resilience that would still look bad from a reliability score. So if they have to shut off power for a region because of forest fire risk, they still want to make sure that people have some sort of local supply so they can run their medical instruments or things like that.
Great. And we have one more. Now, you touched about the infrastructure on transmission building. What is your perspective? Where are we in the US in terms of HVDC infrastructure, building? Do you see there is efforts on that direction? What is your perspective of you being the chair of IEEE HVDC? Could you share some lights on efforts of that working group?
Yeah, so there's been over the last 20 years, there have been a lot of HVDC projects that have been studied. And there's one that is actually, I think, started construction now. It's going from Wyoming to basically the Southwest, that people have been looking at that since 2005 or 2006. And they're finally at the point where they're starting to do construction on that. But any of those run into the same bottlenecks as any other transmission project. There's another HVDC project in the Southwest going from like New Mexico going west that recently had to stop because of some disputes over some of the areas that they were going through for routing it. I think you're going to see a lot more HVDC in the near term actually with offshore wind. And that creates some interesting things. Like I've seen some proposals where you're going to have 3,000 or 4,000 megawatts coming into a substation in an urban area that has no AC transmission capacity going out of it. So you can put in the HVDC, but you still have to have the AC system to support it.
Oh, thank you, Dr. Brian. I think you're almost time. So if others have any questions, please feel free to email at und.c2sr@und.edu. And thank you, Dr. Brian Johnson, for your time this morning. And I think this concludes this session. We're going to